Um, Hello, everyone. This is Multistep Knowledge Distillation, MKD-Ultra, compressing causal language models in multiple steps. I'm Mamon,
Hi, I'm Nilay.
Austin.
and
All
our
right.
mentor is Partha.
So we'll start off with a little bit of motivation. So autoregressive language models are extremely powerful tools, and they're useful in a whole bunch of areas, such as speech, machine translation, and various other sequence-to-sequence tasks. A recent popular example is OpenAI Codex, which is a natural language to code translator powered by GPT-3. And then another one is AI Dungeon, which is another GPT-3 powered video game. So one of the problems that we have is that modern language models are just too big, especially things like GPT-3. They're really expensive to train, to run, and to fine tune, which means that they're pretty much inaccessible for most people, except for the largest companies and institutions. And also they're not really possible to use on mobile devices like phones or laptops. And we kind of want to change that. So basically our goal then is to decrease the model size without losing any performance. So a quick review of what a language model is. We can basically distill it down to a probability distribution over a string of text. So if we have some text like natural language is difficult to model, a language model would basically be able to calculate that probability. And then we can turn that into a predictive model in two different ways. The first one is causal language modeling, which is basically when you have a string of text, you want to be able to predict whatever word comes next. And the second way is masked language modeling, which is when we have some text with missing words, we want to be able to fill in the gaps. But for this presentation, we're going to be focusing on the first one. So CLMs can be really useful for generative tasks, as I mentioned earlier. One example is in speech recognition. If, let's say, we have a phone that's trying to record some audio and it hears it's hard to wreck a nice beach, it can assign a probability to that text and is probably not very likely. It's a lot more likely that the user actually said it's hard to recognize speech. That's maybe more common. So that the language model would be able to assign that to a higher probability. So some background on standard knowledge distillation, or just regular KD. It's a process where we use a larger model to train a smaller model. So the idea is that a student model, which is the small model, might be able to learn better if it knows what the second or third best answers are. So if you see in this example, the teacher, YTeach, gets the answer right, but it also provides some information. Like it really looks like class 2, but it also looks like a little bit of class 1.
Right. So with that being said, we propose two different knowledge distillation techniques applied to the language modeling task. So the first technique is bidirectional knowledge distillation, and the second technique is multi-step knowledge distillation. And we'll be comparing these two methods to our two baselines. The first baseline is just a standard transformer decoder, and the second baseline is standard knowledge distillation. So the motivation for multi-step knowledge distillation is that standard techniques of knowledge distillation make no assumption about the kind of teacher that is teaching the student. And so there presents a problem with that, because then there might be an issue with compatibility with the teacher and the student. So there have been previous work that demonstrate that if the student and the teacher have a large gap in size, then the teacher and the student won't be able to learn as efficiently, and because the transfer of knowledge kind of resembles more of like hard labels rather than soft labels. The other thing to mention about multi-step knowledge distillation is that there's a lot of work also focused on transferring knowledge within the components of the transformer or within the components of the architecture. So on the right, we see this is a diagram taken from TinyBERT, which transfers knowledge from the attention matrices and other parts within the model. But the difficulty is that there hasn't been many approaches that focus on the compatibility with the teacher and the student. So the solution to this would be, or one solution to this would be to train an intermediary model. So X here would be the teacher, X prime would be the intermediary model or teacher assistant, and Y would be the student model. And on the right, we see how the transfer of knowledge is happening over the logits at the end of the model. So, so the logits are being transferred from the teacher to the teacher assistant and then to the student finally. And our second method is bidirectional knowledge distillation. And the motivation of this is that if we look at speech recognition, there's an idea that if we integrated the right context in speech, we'd be able to much better predict the actual speech signal. So this kind of motivation is why bidirectional knowledge distillation is interesting. So on the right side, we can kind of see this being kind of a helpful teacher, where if you had the left context and then you also had the right context, well, maybe it would actually be better to then predict the target word. So the bidirectional language model is essentially taking a pre-trained model, or sorry, it is essentially taking a left context here and then a right context, and then combining them, and then that is what forms the bidirectional model. So a bit of a note on our data. The data we use is Wikitext 103, and Wikitext is basically a Wikipedia set of articles which are considered like good articles. And it contains around 100 million parameter or 100 million tokens, and that is what we'll be using to train our models. And within our experiments, we have we've decided that we want to remain constant with all of the parameters except the layers, which will then form kind of the difference in sizes that we'll have. So in our particular experiments, we trained models which are as large as 16 layers, and that translates to about 140 million parameters, and as small as two-layer transformers, which translates to around 40 million parameters. Additionally, we have some downstream tasks that we then wanted to see how the performance would be. And the motivation for this is that models tend to be underspecified, meaning they tend to have multiple different configurations that produce the same validation performance. So they're not necessarily better or worse, they just encode different inductive biases, but they may produce different generalization properties. And so the idea of testing it on downstream tasks is to see maybe how they might generalize to different tasks. So in this case, we test our trained models on Wikitext on two tasks, semantic textual similarity, and then COLA, corpus of language, linguistic acceptability.
So the evaluation metrics we used for procedures are the following. We had model performance in perplexity, which is a measure of how perplexed the model is by the data set. Lower the better, higher is worse. We have the model size measured in layers. All of our embedding dimensions were 768, consistent with BERT. And then we also measured downstream performance on two glue tasks, and the scores for those, the higher the better. So we have the results in perplexity on the Wikitext 103 data set. And so the best overall model, so the model with the best or the lowest perplexity, was the standard knowledge distillation approach, in which we use a 16-layer transformer as the teacher and a 10-layer transformer as the student. And this accomplished 29.55 perplexity. And then our best 6th-layer, which is notably smaller than the 16-layer, got perplexity of 30.65. And this is the multi-step knowledge distillation. So going to the extra trouble of adding an additional student, which doubles the training time, was well worth it, in that we ended up with a model that was much, much smaller and accomplished a very good perplexity score. We even saw that, right, so this and some, yeah, we'll discuss the analysis of these results in later slides, but this just gives a quick overview of what we saw with these different approaches. Go to the next slide. And so here, focus on the bidirectional knowledge distillation experiment. And so these results were less promising for this approach. And so we see, in some cases, the perplexity goes slightly down. So what we mean by baseline perplexity is the baseline of, or the perplexity of the model of that size. So for example, the first row, 16 by to 6, means we have a 2 times 16-layer bidirectional. So the bidirectional model is comprised of a 16-layer forwards model and a 16-layer backwards model that were trained independently. And we are training a 6-layer forwards model. And so the baseline perplexity is a perplexity of a 16-layer model. And so the fact that we had to go to all of this trouble to get to a 6-layer model that could do 34 perplexity is not exciting, especially when you consider from our previous slide we had a 30.5 perplexity at a 6-layer model. So, and in even some cases, it wasn't even able to properly distill the information. And we could see that perplexity is worse than if we had just trained directly, which is always concerning when it comes to these distillation approaches. So we'll discuss more in detail our analysis on this as well.
So on the 2 downstream tasks, first was the semantic textual similarity. We found that MKD again is quite effective. So on the right, you see a graph. The green is the multi-step knowledge distillation. And it outperforms the standard knowledge distillation and the baseline, which is what we want to see. In the 4-layer case, it actually didn't outperform the standard knowledge distillation. It was close, but not quite. But in the 6-layer transformer, it actually achieved a better performance than both of its teachers, which is great for the approach. One side note for these 2 tasks, though, the STS-B and COLA, we were not quite sure that they trained all the way down to convergence because of the small amount of data that they have compared to the absolutely massive language models. But these are the results we got, and they're consistent in the COLA slide too. So if you go to the next slide, please. Right, so in this one, it's actually more prevalent. The MKD in the green, again, is far better than both of its neighbors, the standard knowledge distillation and the baseline. And again, the bidirectional knowledge distillation is not very effective. It very slightly outperforms standard knowledge distillation, but not by a significant margin. And it almost quadrupled the training time, I think, if I remember right. And I forgot to mention in the last slide, but it actually did worse than the standard knowledge distillation and the baseline in STS-B. Next slide. So in conclusion, we presented the first, or at least to our knowledge, application of MKD in any NLP task. And we also saw that it was a pretty big improvement over standard knowledge distillation, especially in the downstream tasks. So we got better language modeling performance by about 0.5 to 1 perplexity point, a better downstream performance, and all at the same model size. But like Austin said, the cost is 2 times the training size, or sorry, training time, because you have to train the intermediary model as well. One bit of future work that we're really interested in is scaling all this up. So we used a relatively small data set just because of computational constraints. But if we were to scale it up to, say, billion word corpus, we might be able to see some more promising results, especially if the gap in model size is significantly larger. And then the second thing is that in these experiments, we modulated the layer count, but maybe it's more appropriate to modulate the embedding dimension. So instead of keeping it constant at 768, we can bring it all the way down to 256, for example, which will have a pretty significant effect on the model size and theoretically on the performance as well. So MKD might be able to shine there. And then, yeah, go ahead.
Yeah, we were disappointed in our conclusion with the bidirectional teachers, and so we found that their results were not promising. So recall the slide in which we listed the perplexities. We had, for example, a 2 times 16 teacher model and a 6-layer student model, and so that's a very big gap. And so a large gap has been shown to interfere with knowledge distillation, so that could be a barrier. The other like contributing factor to the large gap is that the teacher is too good, and so we didn't mention this, but there's you can look at the pseudo perplexity of the bidirectional teacher model, or just a bidirectional model. And it's referred to as pseudo because it has far too much information to be thought of as standard perplexity, and it's, like 4, for example. In the
I don't mean to cut you off, but we might want to move to our demo because we're running out of time.
Do you want to share your screen, or should I show the video?
Yeah. I think you have to stop first.
Yeah, I stopped.
So this is a Flask application that has all of our models available. It also has our results, which we showed in the slides. These are just all of our results organized. So it's an autoregressive language model. So we have it set to stop generating at 100 tokens, or when it records the end of sequence token. So it's not.
What was the context that you put in? I couldn't quite read it.
Homomorphisms generalize various notions of graph colorings and.
Another thing to note about this is we use a temperature of 0.8, I believe. So what temperature does is it samples from the probability distribution in a different way rather than just taking the most likely token. And what that does on a practical level is it removes kind of the repetition that you end up seeing if you just sample from the most likely token.
You want to try somebody's name?
Yeah, let's try Jane Noah. I have a plugin which it highlights magic cards. Should disable that. Well,
Also, another thing to note is this is, again, from Wikitext 103. So a lot of the predictions are coming from Wikitext or Wikipedia articles.
I'm not too concerned. Usually when you say something positive, it just repeats things that are positive. So hopefully it doesn't, I haven't had an issue with it producing offensive content.
I think the data set's filtered for that.
Team Ford, do you want to wrap up your demo in the next minute?
Yeah,
Yeah,
we're pretty much
done.
Okay.
Yeah.
Yeah, I mean, we could also open it up to questions.
Okay.
You want to go back to your slides, Mamon?
Yeah.
Thanks.
Okay. Okay, thanks Team 4 for the slides and the demo.